Welcome friends. Today we will be covering on two important topics. One is about instruction timing. Okay, I will give you an example how to calculate the timing of a particular instruction. How much time does it take? Okay, because we have discussed so many number of cycles, non-sequential, sequential, and internal cycles. But how do we come up with that number? Once I show you for one instruction, for any other number of other type of instruction, you should be able to come up with that. Okay, and then very interesting topic now addressing mode 4, which talks about multiple load and store instructions. Okay, this is a continuation of what we discussed, LDR and SDR, which was doing only storing one particular register. SDR was doing storing one register into memory, and LDR was loading one value from memory into a register. We discussed multiple ways of using those instructions. Now in addressing mode 4, it talks about how multiple registers could be exchanged with the memory. Okay, it could be from memory to registers or from register to memory. Okay, so these are the topics that we will be covering today. Mainly the first part of the discussion would be to find out how a particular instruction, how much time does it take and how do we calculate it. I will show you with an example a pipeline and what happens inside a pipeline, so that this becomes very clear to you. And then we will talk about the addressing mode 4 using those LDM and STM instructions. Okay, now I am taking examples from LDR and STR and then show you how the timing is calculated. First of all, let us see what is the definition of instruction timing. The instruction timing is the measure of time spent by an instruction in the execute stage. Please remember, this is the time spent by the instruction in the execute stage. You may wonder, why are we not considering the time an instruction spends in the decode stage or fetch stage? Because that is a parallelized operation in the pipeline. Every instruction goes through those two stages. When an instruction is residing in a decode or a fetch stage, there is some active instruction going on in the execute stage. So the time spent by the instruction in the execute stage is what is more important. So let us see how we can calculate it. Now take an example. This we have seen earlier. I used this particular sequence of instructions to explain you what happens inside a data path. Now let us use the same sequence of instructions to see how do we calculate the time spent by the time taken by the store register instruction. So we are interested in this instruction, but it is followed by few add instructions and then it was preceded by one add instruction. Now I want you to think about how much of time that each stage, when multiple instructions are there in a different stages, they take. Okay, now can we guess what is the time taken by this stage? We can say that maybe it is a sequential access of an address, instruction from the memory, add instruction. So you can say that, you may say that it takes a s number of cycles because it's a sequential access, because instruction fetch is sequential. But what I am showing here is the first instruction, right? The first one. I didn't show you what is prior to this. So in this case, we don't know whether this particular instruction is being fetched for the first time with maybe a data transfer prior to this. That means the first cycle would have been a non-sequential cycle. So the possibility is that it could be a sequential cycle or non-sequential cycle, because you don't know what has happened prior to this cycle, because that is not shown here. So we can't make any guesses on how much of time it has taken. Now you may wonder, why are we differentiating between a non-sequential cycle and a sequential cycle? It is very obvious. A non-sequential cycle is one where you are giving a new address and the memory is starting from that address to access it. So the first access will take n cycles, that is capital N cycles, a non-sequential access, and subsequent memory accesses, if it is following the earlier addresses, then it may take S, that is which may be lower than the N. So then we will call it as a S, that is sequential cycle. So in this case we can't predict it because this instruction access could have been followed by another fetch, then it could have been sequential access, but it could have been followed by a data transfer, which that means it will be a non-sequential access. So let us see what is the cycle this is going to take, this particular stage. Though pipeline moves in lockstep, every stage, and it depends on what instruction is there in each stage, and then the maximum time that any instruction in that stage takes, that is the way the pipeline is going to move. In this case, we know that there is a decode here, and there may be an execute of previous instruction in there. Okay, so out of these operations, which would take more time, relatively speaking, anything to do with the memory is what is going to be consuming more, because in ARM, especially in ARM mode, the instructions are structured such a way that the decode takes minimum time. So the fetching an instruction from the memory is what is going to be more time consuming compared to any other operations. So when you have a fetch before, it clearly shows that this is going to be a sequential address from the previous one, correct? So the time taken by this stage will be yes, because this is a sequential address from this, and this memory access is the operation which takes more time compared to any execution or any decode stage within the pipeline. Now come to this. Here what happens in this particular cycle, what all is happening? This fetch instruction, the add instruction is getting executed here in the execute stage of the pipeline, and our STR, which we are interested about, is getting decoded here to generate the signals required for calculating the address within the data path, and then next add instruction is getting fetched. So which is going to be taking more time? Very logically, this is a yes, because memory access is always time consuming than any other operations inside the, but multiplication may be more complex, but in this particular case add gets executed pretty quickly, right? Where two operands are already they are going to be fetched, and you have seen what all happens when a particular data processing instruction gets executed there. It all happens within a cycle. So that's why we call always the time taken by particular this stage is yes. Now isn't it true here? This is also accessing the following instruction. Now you may wonder, how is it accessing it now, this instruction? Because this instruction is completed, so it is exiting the exe stage. So now our str instruction is entering into the execute stage, okay, and the decode stage is busy with the calculating the transfer signals meant for data transfer. So decode is busy with our str instruction itself. So now what happens? The fetch is coming here for the new instruction, okay, because there is one more instruction which can come in. Now this is also going to take yes. Now here what is happening? This fetch has moved to decode because decode stage of str has already done with the job. Now data transfer is busy, the data address data bus is busy with the transfer of data. So instruction cannot be fetched. You know that there is a common address and data bus, and the memory is common in ARM 7. So an instruction access cannot happen along with the data transfer. So fetch is delayed. Okay. So now is it going to take non-sequential cycle or a sequential cycle? The data transfer is not linked with the previous address of the instruction. It will be a totally different address from where the data is getting read or written. Now actually it is a str instruction, it is getting stored, so the data is getting written into the memory, and it is not a sequential address from the previous memory access, which was a instruction fetch. So this is going to be a n. Okay, so please understand this sequence, how we are deciding on whether an n cycle or s cycle is taken by a particular stage. Okay, because this is going to take more time compared to any decode operation that is happening. Now you should be able to guess what is going to be the cycle time here. This is the most costliest in terms of time is fetching, but is it in a sequential access compared to the previous access? Previous access was a data transfer, and now it is going to access an instruction, which will not be in a consecutive address from the data. So the first fetching of instruction here after data is accessed will be a non-sequential access. That is why we see that n is coming here. Remember that, not that every fetch is going to give you yes only. Only when there is a previous instruction is also instruction, then the sequential access is maintained. So it will memory will be able to provide the data much faster than a non-sequential cycle. And in this case, we are not going further down because we don't know what is coming here. Okay, most probably it will be another fetching instruction, so it could be yes, but our interest is on str. So how much time has it taken? The str instruction has spent in the execute stage. It has taken 2 cycles. It has stayed there. One is of type S cycle and another is of type N type. That is non-sequential access. So an str takes 1 S and 1 N cycles to execute. This is the way we arrive at this particular timing. So str instruction takes less cycle than LDR. Why? Because LDR will take one more cycle to move the data that it has read from the memory into the register. We will see that in the next example. So I am showing you an str here. So this offset computation was done by this calculator address, and the actual transfer of R4 into memory has happened here. Now because of this, there is a non-sequential access of the instruction, and this itself is a non-sequential access of data. Okay, I hope now, given any instruction, if you know the sequence in which other instructions are placed inside the pipeline, you should be able to calculate the cycles taken by the instruction. Okay, this will be a good exercise to compute. Now I told you that LDR takes little different timing. Let us see why. Let us first understand what this particular LDR instruction goes through, what all it goes through into the in the pipeline. First, its decode operation is done for this stage where calculation of address, the offset is calculated by the data path, and the address is generated, and now the loading, it is actually loading means it is trying to read from the memory and then put it into some register. So the data transfer happens. Here what is the read cycle or write cycle happens? It is a read from the memory. Now is it going to be a non-sequential or sequential? It will be a non-sequential address because there is no linkage between the instruction getting fetched, the address where the instruction is getting fetched, and the data which is getting fetched in the next cycle. So it is going to be a non-sequential cycle. Now what does this one more cycle take? This is actually moving the data which comes in from the memory into a data in register. If you recall, in the data path there is a data in register at the bottom where the memory loads the value into the data in register. Now it has to go through the ALU and then gets written into the register. Okay, so let me tell you what happens. I have already explained it. See, this is the register which is RD. Okay, now memory cycle has happened and the data in register has got the data from the memory. Okay, from the memory. Now this has to be moved into this through, if you remember the path which was going through ALU, and then barrel shifter is affected, and then the register file it has to get written into RD. Okay, so this whole operation happens within the data path, and it is purely an internal cycle. When this is happening, is there any memory access happening? It is not, because you can't fetch an instruction also because already the pipeline is full. Okay, because this instruction has not exited the execute stage, so you can't access the instruction from the memory. Okay, instruction cannot be accessed, and there is no memory access needed also, because the previous memory access itself is not yet copied into the register. So it is going to be an internal cycle. So let us see whether what I am saying is what will happen now. Here again, the first access we don't know whether it is a S or N, and here we are very clear it is going to be a S cycle. Here it is going to be S, correct, because it is a sequential address. The instruction is getting fetched. Now what happened? This is also yes, because calculating address is a simpler internal cycle which is lower than the sequential access. Now during this data transfer, what happens? It is a non-sequential access. You are clear now. Now this is what I am saying. In this case, there is an internal decode is happening as well as internal transfer is happening. Nothing to do with the memory, either with the internal instruction or memory or a data. So there is no memory cycle. Internally, the processor data is whatever data it has read from the memory is copied into the register, because it was an LDR instruction. So it is going to be an I. Okay. So next will be, here is very important. You should remember this fetch is nothing to do with the previous data transfer. So the first time that instruction access also will be a non-sequential access. Okay. Now how much time our instruction of interest has spent in the execute stage? This much time, right? After that, the next instruction has taken over the execute stage, and prior to this, add was in the execute stage. So our timing is this much. So which is corresponding to 1 S and 1 N and 1 internal cycle. So I hope this is very clear to you. I thought it is very important that you understand it from the pipeline perspective, how an instruction flow through it. Okay. So you can see the difference between an LDR and STR now. LDR takes one more cycle more than STR, because it has to be the data which has read from the memory has to be copied into a register, which involve one more internal cycle. Now I will ask you another question. Suppose if LDR involves something to do with the R15, that PC, what is the impact of that particular instruction? That is what we will see next. You may see that there is a big gap. There is a lot of gap in between. Let us see. Let me explain you what is happening. The instruction what we are trying to address here is some operation is done on some register. Okay, and then a new address is fetched from memory. Okay, let me explain you with a diagram. See, R15 is here. Okay, PC. Now this instruction LDR PC. PC is the RD now. Okay, that is a destination register. It is getting an instruction. Okay, let me give you an example. LDR. Okay, I should have shown that now. Okay, not a problem. R15. Okay, comma. You are doing from R1 comma some 0x. Okay. Sorry, 0x 4. Okay, because 4 is what we have to give, because instruction access are all 4-bit aligned. Now suppose this is the instruction. What are we trying to say? Whatever is the content of R1, okay, add it with 4, because there is no minus here. Hopefully my handwriting is clear that I have not put any minus. Okay. Now assume that R1 was having 100. Okay, for a change I am taking 100 rather than 1000. Now plus 4 will result in 4. Okay. Now this has to be accessed. It is in the memory. Okay, 104 is in the memory. Now we are taking whatever is the content of 104. Okay, some address is here. We are copying that address into R15. So R15, this location is having a address. Okay, from where the next instruction has to be fetched. It is having an address. Suppose it is X, address is X. Okay, at X. Okay, it's a code. It is supposed to be instruction memory. the R15 should start executing from this address. Okay. Now to do this, we have to do this one memory access to read this at 104, get the address, load it in R15, and then R15 should start executing by accessing it from this one. Sorry, it may be not. It is not 104. It is X, some address X, which was read from the 104. Okay. Now let us see how this happens. Now first decode of this instruction was done, and then the calculating address, that is adding with the 100 which was in R1 with the 4 which was an immediate constant, and that address is generated and it is put into the address bus. And now instruction access, actually it could be a data access, because though instruction is saved here, it does not matter, okay, what whether it is an instruction or data memory, because we have a unified memory here. So this transfer is taking place, okay, and then that address which has come in is getting copied into R15. Okay, one internal cycle will be consumed by that. After the R15 is copied, then it will start fetching the instruction. Now will this new instruction which is getting fetched, assume that there is an add here, okay, add instruction was there, okay, normally we don't put add here, but assume, okay, will it get executed immediately? No, because this will sit in the fetch stage of the pipeline, then it will go to the decode stage, and then this is going to get executed. That means the instruction which was changing the R15 is going to spend a lot of time inside the pipeline in the execute stage. It is implied, okay, it is not actually doing anything beyond this, but execute stage is not doing anything during this time. Why? The instruction, new instruction which is getting fetched here, will take 2 more cycles to pass through the fetch stage, okay, fetch stage, then decode stage, okay, and then it will come to execute, okay. So 2 cycles will be wasted in the execute stage. That is why you see there is a gap, because execute stage does not have anything to do. I hope this is clear to you. This is very important. I thought it is, you should be clear with that. Okay, let us see how much time each of them take. Okay, that will give you how the computation is done for the LDR with the PC. It's always any PC is involved, especially in the destination register, it is going to take more time, because we are changing the flow of instruction. Now can you guess what is the time taken by this? Okay, we don't know. Let us not worry about it. Now here you can know, because some other instruction is in the execute stage, and please remember, you may see that you may say, okay, there is one execute stage in one more instruction may be there. Won't it take more time than this fetch? How can you say this will take X? See, if it was a data transfer, then there is a possibility that it will take more time. But if this execute stage was a data transfer, then fetch cannot happen, because 2 memory access cannot happen at the same time. So it will be some another execute inside the processor itself. Okay, that will naturally be taking less time than a memory access. Either it's a sequential access or a non-sequential access. Anything to do with the memory is much more time consuming than anything that is happening inside the processor. So this will still be yes, because we are guaranteed to have not to have any other memory access here, because if that was a memory access, then the fetching wouldn't have happened here. Now how much time does this take? This is already our execute instruction is entered the execute stage now, okay, and what is happening here? It is getting computed, the address offset whatever 104 we were doing, it's getting computed here. So but parallelly one more fetching can happen, so it is a sequential access. Now the data transfer, this is a transfer for accessing the instruction stored at 104, which I showed you last time. So that will be N, because that is a non-sequential access from the address previous instruction. Now that gets copied into R15, which will take one internal cycle similar to LDR we saw earlier. Now this instruction, new instruction at 104 is getting fetched. Okay, the execute stage is empty, it is not having nothing to do, but it is now fetching a new instruction, so it has to be a non-sequential access. It will take one more yes, because now it is the next instruction followed by this, so it will be a yes cycle, and one more here will also be yes. Now what is the time our LDR with R15 has taken? It has taken from here to here, because the next useful instruction gets got control of execute only at this time. So till this point you have to consider that this instruction only has taken up the time. So the time taken will be so much. So how many n and how many s? 2 each and 1 internal cycles. This is what you will see in the manual. So this is the sample instruction. It could be 4 or 5. I put some number, but I actually sorry it should have been 4, because we don't want a odd number address to be given to R15. So then it may be you can do it, but it will involve some thumb mode access. So let us not you are not even aware of thumb mode. So please assume that this is a 4 or some number which is divisible by 4. Okay. Now the interest is this one. Okay, topic of interest is this much cycle is going to take. So when you see this in the manual, you cannot directly find out how is it taking so much time. Okay. Now with this explanation on the pipeline, exactly what is happening, you are ready to validate any kind of instruction. How much time does it take? If the manual says something, you can verify it by yourself drawing this pipeline and then going through each stage and then understanding which stage is going to be consuming more time, like what I did. Okay. So this will be a good exercise for you to do in the lab section or as an assignment, home assignment. Okay. So whenever an instruction changes the PC, please remember it will include additional 2s cycles for the new instruction to enter the execute stage by going to the 2 earlier stages of fetch and decode. So that 2s is coming from this. Now you can make out how it is happening. Okay. So this is the total explanation on what is happening. So with this we are done with the instruction timing. So let us get into a multiple load or store instruction. It's very interesting. Please pay attention to it. Accessing one memory and multiple memories involves some things. Okay, multiple sequential accesses. Let us see. This is the mode 4 we are going to talk. With this, we will be completing the addressing mode discussion, and mode 5 will come later when we talk about coprocessors. Okay. Right. Now, how do you access multiple memory? So when you want to, when do you want to access a sequence of words? Okay. Only when you want to transfer a set of registers, okay, which are inside the processor to memory, or you want to load a set of registers with a set of some data which is stored prior or maybe a new values from the memory into the register. Okay. So it is like you want to initialize a set of registers together in one single memory cycle. That means when I say one single memory cycle means it will involve multiple cycles, but it's all done together, one after the other. Okay. So processor supports that kind of a operation with the load and store multiple. You may wonder why is it required? It is required whenever you are doing a function call, or maybe you want to go to some exception. Okay, on exceptional transfer. Okay, you are entering an exception. Suppose I have not talked about exception yet, but let us see. It is a control flow is totally changing from the normal flow. Now inside the exception you will be using the registers which you were using in the normal flow. Okay, set of registers. So okay, now before the exception or ISR, inter service routine, you uses those registers for its own purposes. You should save the set of registers into stack. Okay. So okay, stack is some memory. Okay, it doesn't matter whether we we call it as a stack or not, it depends on what kind of instruction you use. So this is the exception handler, okay, handler, okay, and this is a normal code, okay, normal code executing here. Now what I said was code is getting executed, suddenly one exception has happened. It could be an interrupt or it could be a data abort, whatever it is. Because of that, it jumps into some new location to execute some set of instructions. Now in this case, it's also assembly code exception handler, and it will be doing some operation, okay, with a register, using the registers. But it has to make sure that it doesn't override some registers which are used by the code prior to the exception. We don't know which register was used, because all the registers, there are some bank registers which I mentioned. Apart from that, there are some registers which are common. So if you are using any of the common registers, you have to save them. So to save it, you will use a LDM or S. In this case, STM you will be using. Okay, STM you will use to save store set of registers. Okay, in a forever bracket, and then once you are completing the handler, you will restore it back and then come back. Okay, come back to the code which you are running. So the code which is there running will not even know that there was an exception and somebody has come and they saved the register content and then did something else and then came back to it. So it doesn't even know, because it is seeing the same kind of register which it had before the exception happened. So how is it managed? By executing an STM and an LDM. Load that set of registers from the memory back, and then before you come back to the normal code. So that is why the LDM and STM are useful, because you want to do the set of registers saved and set of registers restored with one single instruction, which will be much time efficient compared to saving them one by one. If you are familiar with x86 instruction, there was a push and pop A. If you remember, it is similar to this instruction here. Okay, there these instructions were specific to the stack pointer and the stack memory, where it was pushing a set of registers into the memory and then popping a set of registers back into registers from the stack. So this was in x86. Okay, and ARM supports using a LDM and STM instruction which were similar to this. Okay, very good. So load store multiple instructions can increase the interrupt latency. Now what is the side effect of this? Normally the ARM processor do not get interrupted when these instructions are getting executed. It will wait for them to be executed. Abort is different. So let me not confuse you right now, because you are not heard about abort. So when that happens, we will talk about it. So normally when an interrupt happens, there are two interrupts, IRQ and FIQ. When those interrupts happen, they need to be processed. So it has to go into the ISR vector and then process them. Okay, that also I will be covering you later. So it will recognize the interrupts only when after this particular load store is completed, because if it is interrupted, the memory cycle, half of the instruction registers would have been saved by the LDM or STM, then there will be a confusion. So it will complete the load LDM and STM. So normally what happens, if you are executing this instruction, the interrupt latency will be more. What I mean by interrupt latency, you are aware of this, being an embedded software programmer. How much time does a processor take to respond to an interrupt? Actually, in a particular time scale, interrupt has happened, and then it takes so much time to come back to respond to it. That means executing the ISR for the interrupt. So that will get delayed because saving a huge number of registers into memory and saving or restoring them. So if an interrupt is raised, then it has no effect until the load store multiple instructions is complete. So that means the interrupt is not recognized till the load store is done. Now let us see what is the format. Okay, LDM, STM, conditional code, addressing mode, which addressing mode you are using for accessing it, and then you are saying that RN, which is a base register on which you are working on the addressing mode, and then this is something new. Okay, set of registers are given. Okay, in this case, list of registers I will give an example, then you will understand. So when you are storing or doing multiple registers, you have to give what are the registers you are trying to save, whether R0, R1, R2, R3, or which register. You may pick any register and then put it in the list. Okay, whatever is accessible at that mode, then it should be able to perform the job. Okay, so basically a load multiple register consecutive addresses from the memory, contents of the memory is copied into the set of registers what you are given. Similarly, store save set of registers into the consecutive addresses into the memory. So n is the number of registers. Okay, here that many registers are saved or stored based on number of registers in the list. Any subset of current bank of registers can be transferred. Okay, there is no limit. You can give 1 or n number of them. 16 are there, maybe you can give 16. But at least one register should be mentioned in the list. You cannot give an empty list. And a base register is Rn. So from where, which memory, starting from which memory address you want to store them, all the registers. Rn register can be optionally updated also. So after this transfer, if there is an exclamation mark, that means if you recall LDR SDR has this exclamation mark to say that a write back happens. So the base address can be modified after the complete transfer of the instruction is data is done, multiple data. So one more thing you have to remember, Rn, which is the base register, can also be mentioned in the register list. Okay, there is no verification of these two by the assembler or the processor. Okay, so what is the effect of that? When I am showing an example, I will tell you. You are trying to use the one of the registers as a base address to access the memory. At the same time, you are modifying it also as a part of the save or a load. Especially when you are modifying it with a load instruction, then there is a undefined behavior is possible if there is a order in which you are doing it. Okay, so be cautious of giving the same base register into the register list also. It's better to avoid them. Okay, so don't have to spend too much time here. The conditional code is here as usual, and there is a special 100 which is meant for this. And then you have seen most of them, whether pre-indexing or up or down, whether the memory is going up or down. And then there is one special bit here which I will talk about. This PSR is a status register which is unique for the LDM STM, which will be used only in the exceptional mode, the privileged mode. So let us not worry about it right now. Okay, remaining thing is the register list. How many bits are allotted? 16 bits are allotted. Why? If there is a 1, that means you are interested in either loading or storing that particular register. Okay, or 0 register. If there is a bit 1 is set, that means R1 you are interested in loading or storing. So you can mention in any register from 0 to 15. 16 registers can be mentioned by giving it in the list. Okay. Now, how do you use this instruction? Register list is there, but there is a qualifier which is given here. Okay, this talks about how to change the base register after one access, every access of the consecutive addresses. Okay, so please hold on. I will talk about this in the next slide. Now, what is this? Okay, this you understand, but what is this caret symbol? This is very specific to the privileged mode, exceptions are SWI. So we need to wait till we come to that stage. So please ignore this for a moment. Now this I will be talking about it in the next thing. Now I want to give you an example first before I tell you what this instruction does. Okay. Now you remember that our convention, right? This is the registers which are set with its values, and this is the content of the memory before our instruction gets executed. Now I'll explain you LDM. You understand it is loading. It is loading what? Loading into the registers given in the list. How many registers are given in the list? If you mention a hyphen here between two numbers, it includes all the registers that come between them. So R1 to R15, how many registers are there? R1, R2, R3, R4, R5. 5 registers are given in the list. So in the instruction format there will be 5 ones in the relevant points. Okay, bit 1 will be 1 to bit 5. Now from where is it taken? You are loading from the address where R0 is pointing at. Okay, but before we take the address, there is some command to the instructor, the processor say that, hey, before you take the address mentioned in the base register, increment after. That means you are supposed to, the processor is supposed to increment the base register after the first transfer is done. Understood? So the processor is supposed to access the first word pointed to by wherever R0 is pointing at, okay, pointed to by R0, copy that into the lowest register, okay, whichever is given, R1 to R1. When I say lowest, means the lowest in terms of number, and then the address from where it is supposed to take is the lowest address. Okay, I will tell you why this restriction has come in. So R0 is giving a base address, and then it is going to vary from increment after. That means it is going to change from 1000 to some address based on number of registers that are there. But it says that increment this register to access the next element after you access the first one. That means 1000 wherever whatever is the value comes into R1, okay, and then R2 is accessed, R3, R4, R5. I put the values such a way that they match so that you understand what is happening. Because it says increment after, so after the loading it is going to be incremented. So after the fifth value is copied into R5, it is going to be incremented. So the R0 value will be 1014 after this execution is done. Okay. So please remember, when you have multiple registers to access, the address has to be modified. Otherwise, you will be accessing the same address to you will not get change anything, right? You will be overwriting on the same location. So if you are accessing multiple values, you have to increase the address or decrease the address so that you access every time some different values. So that is implicit. Now, how do you increment it or decrement it? Whether you will start incrementing first and then loading the value or storing the value, or you first load and store and then increment. So if you remember, recall in the second session or so, I talked about stack can be changed in different ways. So that is what is implemented here. Please remember, there is a different instruction. Four possibilities are possible in this. So I hope this example is clear to you. With this, let us go and see what all different things the base register can be modified. So the base register can be first incremented, increment before or increment after. So the example what we saw was this, increment after. Okay, so it access that location first start address wherever the RM is pointing at, and then it incremented the value to access the next element if it is there in the register list. That is why you see the start address is RM here. Whereas if you say increment before, whatever is the base address is, please increment it first and then you access the memory. That's why the start address will be +4 in case increment of before was given along with the instruction. Similarly, decrement after. Now again here, why is it a minus here and then a actual value here? Here you remember, always the processor accesses from the lower address. Okay, let me give an example. Suppose you have memory, okay, our favorite address 1000, and there is a 1004 or 1008. Okay, let us take only 2 registers you are getting transferred. Okay, now assume for a change R0 is our base register which is pointing at 1008. Okay, and then you are saving, you are given a register list saying that R5, R6. Sorry, I don't have space here, so please forgive me. It is 6. Now, what are you trying to say? I have two locations in the memory, which is pointed by R0, okay, which is pointing at 1008, and then I am telling also, okay, in the decrement after. Please remember, I am saying decrement after. What am I trying to do? We can do LDM or SDM. Let us say LDM. Okay, I want to load, okay, two memory locations. 10 is stored here, some 11 is stored here. No problem. Now, okay, you have to combine all these things. Okay, LDM decrement after. Okay, load means what? You are loading from memory to register. Which register? Our friends are here. So okay, let me show this register R5 and R6 with the values which are at 1008 and 1001, which are expected to assumed to be having a 10 and 11 values. Now currently the base register R0 is being used, which is currently pointing at 1008, and I am telling the processor decrement after. That means what? You access this location first, okay, and then you decrement it, and then access the next location, and then copy into R5, R6. Let me ask you one question. Which value will go into which are the registers? I told you the registers are accessed from lower numbers, okay, and the addresses are also accessed from lower address, okay. I'll ask you why it is, but for a moment assume that address is also from lower first, and then registers also copied in the order in which R4 lower register numbers are copied. So in this case, which is the lower address? 1000. In this two register, which is the lower register numbers? R5. So this is the way it is implemented. Okay. Believe me, R5 will get what? 11, because it is going to access from lower address, and R6 now it is very trivial to say what will R6 get. It will get 6. Sorry, 10. Right from here. Now this is the way. It was a decrement after, so it is happening like this. Now let me give you another scenario. Okay, R0 is having the same thing, and your list is also same. Your LDM is same, but I changed this one to decrement before. Now let me ask you. Okay, when everything being same, what will decrement before do? Think it over. Tell me. So decrement before. So the execution is going to start, but I am saying a decrement before. Where am I most here? Okay. So it will be decremented to 1004. Okay. So this is 8. This is 4. Okay. This is 1000. Okay. Where is it? Oh, I'm sorry. I made a mistake here when I said there is one more value here. So please remember. Okay. 1008 is this. Okay. Oh, this I said R0 was having. What did I say? R0 was having 1008, correct? Correct. Okay, no problem. It accessed these two. Okay, 1000 is having 12 here. Okay, so it went from this to this. Okay, no problem. So far so good. Now I am saying decrement before. That means whatever is the content of R0, you decrement it before you access the first value. So 1004 will be the first access. That means the one of the accesses, and 1000. Now the range is between 1004. Okay, because you are given only two registers here, R5 and R6. Now tell me what will be the values in R5 and R6. Can you guess? Don't make a guess. You should be sure about it. Again, remember the processor will start from the lower address, and again remember that the processor will start filling from the lower register. That means 12 will get filled into R5, 5, and 11 will get filled into R6. So that's the way it is implemented. Why? Let us wait for a next slide. Okay, I hope this is clear. So you can do it either decrement or increment after or increment before. There are 4 possible ways you can change the Rn, and it is very trivial to find out how these values are mapping onto. Okay, I don't want to explain because it's very obvious. I want you to do as a homework. Okay, now let us see. Here n is the, let me take the mouse back, where n is the number of registers. This n, okay, you have to come out of that n being a non-sequential access here for a moment. This, in this particular slide, it talks about number of registers which are in the register list. Okay, and based on whether Rn is a base register, whether the Rn is pointing at a data value or not, the end address of the access is determined. Okay, so whether you are doing based on the decrement or increment, you have to see first what the processor does is, based on whether increment or decrement is given, it finds out the range of addresses within which the transaction has to happen, and then it decides which one to copy to which register based on the list. So the register is transferred in the lowest to highest, okay, registers. So R15 will always be transferred last. Why they have put this lowest to highest? The reason being, suppose you have mentioned set of registers R1 to so many registers dot dot dot, R15 also you have mentioned, that means R15 is a special guy which is a PC. So at the end of the execution only R15 will be changed, because the flow will change once you modify this, and if there is a data buffer, there will be a crucial impact of restarting the instruction, which will be clear to you when I explain the data buffer. But for a moment, assume and believe that you have to access it from the lower to highest, because R15 is the PC, and the instruction should not modify the R15 before any of the other registers are modified. Okay, so the conventions are like this. Okay, let me remove this so that you can read the message, right? So the lowest register gets transferred first, and from the lowest address. Okay, this is very important, you should remember. Now some more, and then order of register transfers are not based on the order in the list. This is another fine point, where you have, suppose I mentioned R2 and then R0 and then R5. Okay, suppose this is the order where registers are given, maybe of course comma is required, I think. So the assembler will not crib, it will not give you error that you are given some random order. If you recall the instruction format, it only keeps 1 bit for each register, right? 0 to 15, it keeps 1 bit to say which registers are getting transferred. So R0 it will set 1 here, R5 it will R2, R2. So R2 will be here somewhere, here R5. So it is not maintaining inside the instruction. It is not maintaining the order in which you are given them. It only knows that you are given 3 registers in the list, and then based on this particular condition, always the lowest registers are transferred first compared to the higher register. So whatever order you give here, it is going to transfer the contents from starting from R0 to R2, then R5. That's all. From the lower address to the higher address, whichever is pointed by Rn, based on this type of increment or decrement. So because it doesn't maintain any order, it is not possible for the processor to do that, and it is not making sense also. So it always does it from the lower register order to the higher register order. So you can free to give anything, but there is no order maintained, and there is no need for it, because this instruction is executed in as a particular chunk. Okay, so no other instruction can come in between also. So these are the important points. I think now we are ready to see some examples. I'll ask you one question here. Okay, think it over, pause the presentation, and then choose one of the options. I want the students to discuss among themselves and then decide one of the options. Then you should convince your, if suppose a student A and B are sitting, and then A says it is option is C, and another guy says B, because he is B, he may say B. Now both of you should discuss and then convince each other, and then finally you should come up with one answer. Okay, Could be correct or wrong, doesn't matter, but at least you would have spent some time in spending about discussing about this topic. Then see what is the actual values. The teaching assistants need to take care of this. Okay. Now tell me what happens here. Why is the LDM STM always start loading, okay, or storing from the lower to higher address and also pick the lower to higher register numbers from the list? Okay. So though I have mentioned R15 is the end, so I have mentioned here, so you can always say that this is the right answer, but I want you to unbiasedly, be unbiased about choosing the options. Okay. If you know memory pretty well, okay, the sequential accesses always happen from a lower address to an increasing address, right? So the option is B. Okay. So to enable sequential accesses with memory, it starts from the lower register numbers to say, okay, that is the first reason. Okay, why it is starting always from the lower address, and then it starts from the lower register numbers because they want to change the R2 pin at the end, so that aborts can be recovered from. Okay, sequential memory accesses. Okay, yes, with memory expects the address to be increasing. So LDM HTM needs to start from the lower address. See, suddenly you cannot tell the memory, hey, I am going to give the address, but now you should start decrementing your addresses and give me the data. Maybe the memory controllers are advanced enough to do that, but that will involve lots of other changes to the whole circuitry and the, in the way the processor is connected to the memory. So to bring the uniformity in the implementation, this ARM7 TDMI follows this particular convention, that it will always access from the lower address to the higher address and copy from lower register number to the higher register number. Okay, I hope this is clear to you. The reason being this. Now let us see few examples so that you understand this instruction fully. This we have already seen with the 5 registers in the list. Now I am giving you 4. It doesn't matter. They do the same thing except that it will copy only 4 and then the end address will be this. Okay. So what will be the value? It will be changed from, I am giving you the registers in this order because R1 will be written first, R2 next, then R3, R4 in this from lower address to higher address. Now I am giving you another instruction. I want you to just stay and then look at this and then tell me what happens. By now you should have realized IB means what? It is increment before. Okay. That means we want the R0 to be incremented before any transfer is being done. So wherever the R0 is pointing at 1000 is incremented. So it will, please remember, any increment or decrement is always 4. What is the word transfer we are doing? We are doing always word transfer. There is no byte or half word here. LDM supports only word transfer. Please don't confuse this B with the LDM, STRB and LDRB. They are different. Okay, this B is not for mentioning that it's a byte transfer, it is for increment before. LDM always does a word transfer. Okay, so R0 is incremented and then the R2 to R5 are copied. Okay, from the lower address to higher address. So it's very straightforward. I don't need to spend more time here. Here let me spend a little more time because you need to absorb the instruction. Add R0 with 10. What are you doing? Incrementing R0 content. Okay, R0 you are making it point to 1010. So you are starting from somewhere in the higher address, and then you are telling the processor, I want to load multiple values starting from R2 to R5. These registers should get some multiple values from the memory, but I want you to take the R0 as a base register and please do a decrement of that. What does it mean? You are supposed to decrement the register base register, but do it after you transfer the first word into the first register what I have given you. Okay. Now tell me whether will it start accessing from 1010 or 1000, because it is supposed to provide the memory with a lower address. For it to go from lower to higher address, it has to compute from where it is supposed to access the first location from. Now how many registers are there? R2, R3, R4, R5. 4 registers, right? And though the R0 is pointing at 1010 now, decrement after is given. So you have to start the memory access from 1004. Okay, let me explain you this little bit. Why you should know by now. See, this is the way the access is happening, because I told you that memory can always increase the next address and then give you the data, right? So, but it should know the range. It could be from 1010, okay, to 1004, or it could be from 1000 prior to this what C, right? 1000 C to 1000. How does it know this 4 values, whether it is from this or this, based on whether it has a decrement after or before? Okay, here it says decrement after. That means it is interested in accessing some data which is pointed by this address now. So that means it should make sure that this is also included from here to 4 words. So from 1010 to 1004, what are the addresses? 1000C, 1008 and 1004. That's all. 1010 also. So this is the addresses it is going to be accessing memory from. So this will come first to R2, then from here R3, R4, R5, and then it will lie the decrement after, right? So after the last access is done, it will decrement one more. That's why you see that it is pointing at 1000 now. If you understand this, you should be able to give any combination and try to give the different transfers. Okay, hope it is clear to you guys. I've spent a lot of effort in explaining this. If you don't follow, please go back, listen to this again, make sure you understand. Now a small change, decrement before. Okay, I am showing you both examples of incrementing and decrementing. So it is starting from 1008, okay, up to 1000. Is it how many registers? R5, R6, R7, R8. So luckily this is also 4 registers. So this set of 4 will be accessed, because it says that decrement before you do the first transfer. So then processor will know, okay, I need to transfer between this two and this. Now let me give this to a address register. Okay, address register means which is within the data processor, which is the data path. Okay, so the access will start from 1000, and then it will inform the memory that it's a sequential address. Every cycle it will keep saying that, hey, access one more. So it will access plus 4 starting from here. Starting from here it will be plus 3. Okay, 4 will be accessed, and then every transfer it will know from where to save, because it has ordered the R5 to R8. Whatever registers you are given, it will put all this into bits it has already put. So it will know that, okay, these are the bits which has to be copied. So those registers will be enabled to accept these values coming from the memory. So it is very simple. That's what happens inside the processor. A sequential access is started, and then the transfer starts off. Okay, then these registers will get loaded as I shown you here. And then where does R0 point to? Okay, now one second. So decrement before. So sorry, this should have been 1000. Okay, I'm sorry, this I missed it, because after all the decrementing is done, the last address would be not 1010, it should be 1000. Okay, because this exclamation is there, so this is 1000. Okay, good. So these kind of mistakes, if it happens, you should be able to find out. Okay, I am intentionally doing that. This is the way to explain. Okay, good. So now very interesting part. How are we going to find out the timing required for this? So do you know whether it's S or N? You don't know. Is it going to be S or N? You should be telling right now. Yes. Is this going to be S or N? Okay. What about this? This will also be yes. Now what will be the first transfer? Okay, happening? Will it be N or S? Is a new address from the instruction, so it has to be what? Starting with N, ending with how many S? In first access, if n registers are to be accessed, the first word would have been accessed, isn't it, in the first n cycle itself. So n minus 1 s cycles will have to be, I told you, plus 3 I told you that last example. So n minus 1 s should have been generated to access from the memory or to load it in the memory, whatever it is. Okay, this is the time taken. Now this is the interesting thing. Will it take how much of this? This has to be last register is copied. The intermediate registers are copied while the data transfer was happening. Can it happen in parallel? Of course. Data transfer is something to do with the memory and the data and address back, and moving a register content into the register file is an internal operation. So that can happen in parallel. I am not showing it here, but it is all the registers are saved except the last register which gets transferred. So that will need one more internal cycle. Okay, and then this will be, again, be careful. Don't look at the fetcher and then say it will be S cycle. It will be a n cycle because it is something different from what the previous access was. It is to do memory. It was to do some data address, and this is some instruction address which is non-sequential. It will be, to start with, it will be non-sequential. Now tell me how much of time it has taken. This our LDM n register. It has taken from this cycle up to this part, right? So starting from this is the, you see, one internal cycle, one n cycle, and n minus 1 s cycle. Okay. Now why is it n cycle here? Because there is one s here also, so it will get cancelled, and then you will get a n cycle. Okay. So this is what happens. When you see this, it is not very obvious to make out why the ARM manual is saying this, right? But this will explain you why it is so. Okay. I hope this is clear to you. Now a little difference here. Okay. I told you that there are set of store instruction and set of load instruction. And I told you also that the intent was to save something, a set of registers, and then restore them back into the registers back. Okay. Now, if you need to do that, there should be some order in which you should use the HTM and LDM. You can't do it in a random order. Okay. Let me show the example. Then I'll tell you why they match. One will match with the other one. Assume that HTM increment before was used. Okay, R0 was 1000, and then you said that increment before, that means you access from 1004 and then copy into now store. Okay, you are storing the value what was there in R2, R3, R4, R5 into memory. See, earlier, one second, this was like this. Now after this execution it has changed. Why? Because you wanted to save from R2. So please remember, saving also happens from R2 to R lower register to higher register, and from the lower address to higher address. So R2 will go and sit here, and this is the order in which the memory is updated. You used increment before. Now I'll ask you another question. You want to load. Assume that R0 is now pointing at 1010. You want to load those values exactly back into this registers after some exception handling or whatever, or you got into a function and then you did some operation and then you want restoring all the registers. Now you are giving the same list R2 to R5. Okay. Of course, if you don't give it, it will be copied into some other register. But assume that you are giving the same register. Which load instruction, the LDM instruction, would you use to get the same value back into those registers? Just intuitively see, increment before it was. Okay. So it was incremented before accessing this. So it would have gone and stood here. It is standing here. Now you want this to be copied into where R5 back, right? Now you should not do LDM. Anyway, you have to do a decrement, but you can't do a decrement before, because if you decrement before, you will skip this value. You can't get it anymore afterwards. So it should be decrement after. Then what will you do? You will copy this, and if you give the same order R2 to R5, that means the lower register will get the lower data, and then higher register will get the address in the higher address. So R5 will get this value, and R2 will get this value. But you have to use a decrement after. Okay, I am using that properly. I am using the same R0 because assume that R0 is not changed when you are using, after using this you are using this. By the time R0 is same, you are giving the same list, then it will come here and the exact same value which went out will come back here, and then you can start go with the processing. So that is why these two are mapped. That means if intentionally if you are trying to save something and send set of registers and then restore it back, you should make sure that the base register is undisturbed, and then you are also using the paired STM and LDM so that the intended operation is performed. Processor doesn't stop you from using anything else. Okay, please remember, it is left to you how you want to do it. And similarly, don't think that you have to assembler or somebody will come and help you to see whether you are put the same registers in order or something. No, it's also left to you. You have to take care of that. So writing assembly code is always time consuming, and you have to be very careful in what you are doing. Okay, you can intentionally put some other register to transfer these values into something else. Okay, that is perfectly allowed. So I leave it to you, okay, as a home exercise to see how these two are mapped. And I want you to write programs saying that these two are mapped and then it behaves the way it is supposed to using the simulator. Okay, I can't explain everything here. I think one will make you think. Now we are going into another small stack operations. ARM architecture uses the load store multiple only to carry out stack operations, not stock operations or whatever. So pop operation, removing data from the stack. You know pop and push. So pop is pop out from the stack. That means it is a load multiple because from memory to register. Similarly, push is from registers to memory. So you are storing it. So similar to push, it's a store multiple operation. So ARM doesn't have any pop or push instructions in the ARM mode. It is there in thumb mode, which we will talk about later. So you have to use LDM only and SDM only to achieve these operations. So I explained to you the stack can grow in different ways. It can be towards ascending address or a descending address, or a stack can point to a empty location or a full location. So if you are going up or down, you have to use the A or D operations. Okay, ascending or descending in the stack. Okay, so I'm telling you stack can be operated in 4 different ways, right? If you recall, the SP can be pointing at a full location or it can be pointing at the empty stack. So you can read it out. When you use a full stack, the stack pointer is points to an address that is last used or full location. One example I will show you so that you understand. Stack is here. Okay, you have a freedom to use whether stack has to grow upward. So always this is a low memory and a high memory. So you have a freedom to move the stack in this way or this way. Based on that, you can choose the proper instruction. Okay, decrement after or decrement before or increment or whatever. Similarly, you have another choice whether you want the stack pointer, whatever it is, R3 R13 is on default, but you could use any register also to perform the same thing. So if ST is looking at filled data, then you will normally do, before pushing any data, you will do, suppose you are doing in this increment, the increment before you will do. Okay, increment before pushing the data, because it is already pointing at a full. That means it is a valid data is there. You don't want to overwrite on that. So you should increment the stack pointer before pushing the next element. Similarly, if you want to pop the element, you have to say decrement after. See, it is very easy, easy way to see which are mapping. Increment is there in your store. Okay, LDM has decrement. For increment, decrement. If it is before is there in SPM, it will be after. Okay, it's very easy to map them, but I don't want you to mug up like this. You should know the reason behind it. Okay, no mugging up will help you anywhere. So please pay attention to that and explain it. Reason it out. Whatever you are learning, reason it out. So ascending and STM will go up or down, LDM will be down. So if ascending, okay, if I say that a stack is growing ascending, then STM will go up. Why? When you push something only, the stack is growing, right? So if it is ascending memory, the stack is growing towards the increasing memory. That means while STM it will go up, while LDM you are popping it from there, loading the register from the memory. So you are reducing the stack content. So the stack will go down. Okay. I hope this is clear to you. So instead of using these operations, increment before or increment after, you could use the stack. Okay. See, FA, FD, EA, ED. These are all the same operation which I mentioned to you. Full after ascending, full descending, or empty ascending, empty descending. Whether stack is pointing at an empty location, and then it is going in which direction. Whether it is pointing at a full location and then going in which direction. So these are the instructions which are mapping instructions. So you could use LDM FA. Okay, I will explain you only one, and then you should be able to reason out other things. What is LDM FA? You are loading. Okay, what do you mean by loading? You are popping it. Okay, this is a pop operation. It is mentioned there. Let us first see. It is all mapped. It says so. Let us see whether it is correct or not. First, let us do a push. Okay, you cannot take any value from stack without putting something into it. So let us do some push. That means you are doing a STM IB or STM FA. Okay, it says that they are all equal. So let us see increment before. So you are pushing something increment before. That means what? Increment before is you are pushing. Pushing means stack is growing up. So it is a ascending stack. Very good. That's why you see that ascending is mapped to this. And then increment before. That means it is pointing at a full location. Correct? Otherwise they wouldn't have incremented before. So before pushing, that means it is a full. That is why you say full ascending is what is stored, is the equivalent to the IB. So why they have found similarly the IB is replaced with a DM and while LDM. Why there is a common acronym given to you? You don't have to worry whether you are which IB or AA whether I have to use. Okay, this will be simple. If you say LDM FA, you have to use SDM FA. If your stack is implemented as a full ascending, you should always use LDM FA and SDM FA together, or you could do any other combination of stack operations. Okay, so actually they perform the same thing. All these instructions are same. Only thing is for the usage perspective, they have given you options. You can use any one of them, provided you pair them up properly. Otherwise, you are likely to land up in trouble. What you put is not going to be getting back from the stack. Okay. So one example I will show you. Okay. Let me come back to the moves. Okay. Now you see, I am taking this first example. I have used STMFA. Okay. This is the one. This line is same. What am I doing? I am doing a store operation. Okay. First, before doing anything with the stack, I want to do store operation. You see that R1, R2, R3 were having this value. Prior to this memory was like this. Now it is changed to 11, 12, 13. Why? Because it was the full ascending. That full ascending means wherever it is pointing is already a valid value. Somebody else has pushed into the stack, so you should not disturb this. So it is incremented before and then loaded. All these three values are loaded. So R1, R3 will come and sit from the lower address to the higher address. Now, what is the mapping LDM FA? If you do the same thing, if you do SP is also not disturbed. After this, whatever is the SP value, you should also have that. Then this instruction will do the same thing. Please remember this when you are using, you can use SP here. Okay, that means you are doing a stack operation, so that it will be very clear to you. But you are not restricted to only use SP here. You could use any registers. Okay. If you are compiling a program and then linking with your assembly code, it is better to follow some convention. So R13 is usually used as a stack pointer. If you want this to work with a third-party tool generated assembly code. Okay, this is the example. I hope this is clear to you. This is how you store into the stack and get it back from the stack. Okay. One more example. Okay. I want you to please it and then try what is happening. See what is happening here. See R1 to R14, and then it is saying that empty decrement. What does it mean? It is pointing at an empty location. So you decrement it after you fill the value because it is already empty stack location. So a valid value is put into the stack, but which one is put first? Because it's a higher address, from this to this only it will be saved. So R1 is pushed later, but R4 is here. Okay, that means actual memory transfer will happen from here to there. So R1 will first come and then the transfers will be happening, but the values will be like this. Okay, and the mapping SDM ED is this one. Okay, SDM and LDM ED is this. It will do. It is ED is what? Okay, where is SDM ED? It is similar to SDM DA, decrement after. Okay, sorry, LD, increment before. That means when you are for matching LDM ED is LDM IB. That means it is pointing at the empty location before picking any value from that increment before. So you have to increment the stack pointer before accessing the element in the stack. Okay, so we are coming to the end stage. So there is a possibility of stack overflow. Okay, so how do we handle that? So I am just giving you a sample example to logical conclusion of stack operations. So basically these are the stack base, the Rn, and stack pointer, which is R13, which is the base address, and then the pointer which register, and limit. Okay, beyond which the stack should not grow. So stack base is the starting address of the stacks in memory, and pointer is where exactly current stack pointer is pointing at. It could be growing in descending or ascending mode, or it could be it doesn't matter. Okay, it is to do with some operation while doing the stack operation. So when this is crossing the limit, the stack limit is normally kept in a dedicated register, which is R10 conventionally. Assume that you are keeping a limit, where this supposed to be stack should not grow beyond that. You keep that in the R10 register. Then how do you make sure the current stack pointer, when it pushes, okay, you have to check the stack limit only when you are pushing something into the stack, whether it is crossing the limit or not. See, for example, your stack is here. Okay, this is the total stack size allocated. Stack base is this. Okay, it is starting from here. Assume that stack is going this way. Okay, now currently stack pointer is somewhere here. Okay, now assume that this is the size. Assume that there are 4 words available before the limit is crossed. Now you are executing a push instruction that is similar to some STM. Okay, operation. That means you are going to close the stack more when you are pushing something. So that time you are trying to see whether it is crossing this limit or not. So this is the size by which you are incrementing it, and stack pointer is currently pointing at the current value. So what you do is, after the addition of the size, whether the limit is actually here. Okay, R10 is here. So please remember this subtract and add, whether you are using this, depends on whether stack is going down or up. In this example, you have to assume it has to be going down, so that you are subtracting the value. So okay, if stack is going down, you should not grow beyond some value. Okay, that's why sub is there. Add you have to put if you are going up in the stack. So you are limit the current stack pointer, and then whether it is going, if suppose some size is subtracted from this, whether does it cross the limit or not. Okay, that is what is checked here against this R10, which is pointing at the last location, which is lowest address beyond which the stack should not grow below this. If it is lower than this, it's a stack overflow. So there is an exception handled. So this is the way a special piece of code can be put to check the limit. Okay. With this, we have come to an end. I hope this session was useful to you. Lots of new concepts you have learned. Try out everything, and I'm sure you will become an expert in assembly programming, and also in the bargain you will learn everything about ARM processor. Okay. Thank you very much for your time and attention, and wish you all the very best. See you in the next session. Bye bye.